We're going to take a look at two-sample hypothesis testing, starting with a confidence interval for two-sample means. This is going to give us a way of setting up two different statistical values so that we can actually test them as one. In this first example, we have two random samples of 30 individuals each. One sample was told to jog at a brisk rate. The average breath rate for that group was 19 breaths per minute. The other sample just did normal walking. The mean breath rate for that group was 13 breaths per minute. The population standard deviation for both is 4.3. We want to find a 95% confidence interval. As we're looking for confidence intervals, we want to find our point estimate. The problem here, let's call joggers group 1 and walkers group 2, is that we have 2 point estimates. We have x bar 1, the sample mean for the joggers, and we have x bar 2, which is the sample mean for the walkers. So instead of looking at these individually, we're instead going to use as our point estimate their difference. So their difference is going to be x bar 1 minus x bar 2. And in this case, we're testing the sample difference of 6. So as we're looking at these, instead of looking at individual means, we're going to be testing the difference of means, and we'll also do a proportion example where we test the difference of proportions. So now we can go into this 95% confidence interval. We want to find the values that are in between the actual mean difference. If we were to do this with several different groups of walkers and joggers. I'm just going to put this right into my calculator. So I'm going to go to Stat and then over to Tests. We're looking for now a two-sample interval. So as I move my way down here, the intervals start at number 7 on my calculator. And there's the two-sample Z interval. So I'm going to go ahead and choose that two-sample Z interval. I do have statistics, and I go ahead and put my values in. So I've got 4.3 for both of my standard deviations. Make sure I read the order of these prompts carefully. My first sample mean is 19, and that sample size is 30. The second sample mean is 13, and that sample mean, or that sample size, is also 30. And I do want a 95% confidence interval. I can leave mine at 0.95. You can type over yours if you need to. And I end up with, this is my confidence interval. So I've got 3.8239. I'm going to call that 3.83. And on the other side, 8.176. So that would be about 8.18. So I'm expecting their difference to be between 3.83 and 8.18. If I were to put this along a number line, 3.13 would be about here, or sorry, 8.3, and then we can put 8.18 here. Let me highlight this so we can talk about how this relates to our hypothesis tests. So what we found is 95% of the time, so we have a 95% chance that any groups that we grab are going to have a difference between 3.83 and 8.18. So what we are not expecting is a difference of 0. This would be where the breath rates are about the same. So we are expecting those breath rates to be somewhere between 3.8 and 8.1 breaths per minute different. Let's go ahead and look at number 2. So let's say that we also ask the walkers to go at a brisk rate. And this changes the mean breath rate for the walkers to 18. So now I've changed my sample mean for the walkers to 18. Same standard deviation. Let me go back to Stat and then Tests. And I'm going to grab that confidence interval for two samples, so the two-sample Z interval. I'm going to leave everything the same except the mean for the walkers, and that changes to 18. So remember, I'm testing that difference. So right now, the point estimate for my difference is 19 minus the new 18 rate for the walkers. So my point estimate right now is 1. So as I build this confidence interval, confidence level is still 95%, I end up with this. I get negative 1 point, we'll call that 1.8, that's negative less than the difference, less than 3.1, we'll call that 8. So if I put this now onto a number line, I've got negative 1.18 here, and then 3.18 here. So I would expect 95% of the time, if I grabbed groups of 30 walkers walking briskly and 30 joggers, that the difference would be somewhere between negative 1.18 and 3.18. In this case, I'm going to grab my red pen. In this case, 0 lives in the interval. 0 is where there's no difference. That's where the difference would be equal to 0. So there is a chance, so here, there's a chance that these rates, let me do mu. Mu1 minus mu2 equals 0, or that the breath rate for the joggers is equal to the breath rate of those brisk walkers. So I can use the confidence intervals to also answer these kinds of questions. Do they differ significantly? In number 2 with the brisk walking, no, they don't differ significantly because I found that 0 was inside of my interval. In number 1, do they differ significantly? The answer here would be yes, they do differ. They do differ significantly because 0, where there's no difference, is not within that confidence interval. We're going to continue to work on the confidence intervals as we go through some testing examples. When we translate all of this into a hypothesis test, we're going to change it into, again, a difference of means. This will always be our null hypothesis equals 0. And then our alternative hypothesis, I'm testing the difference again, but it's going to be either greater than 0, less than 0, or not equal to 0. So we've got these 3 different possibilities. As I put this under a normal curve, my expected difference lives right here in the middle. And again, we might have a one-tailed test or a two-tailed test, but we've got a significant difference out in my tails. So I've got a significant difference there, and if I happen to have a tail on the right, that would give me another significant difference. And in the middle, no significant difference. If I write this in terms of rejecting or failing to reject my null hypothesis, in the middle, this would be fail to reject the null hypothesis. If I fail to reject the null hypothesis, that means I'm keeping it, right? That there's no significant difference. They're about 0. But if I'm in one of the tails, I'm rejecting the null hypothesis. Reject. Okay, so we've got a nice little review of those rejection regions and fail to reject region, but we also have it now how it applies to these differences. So again, we can do 2 samples as long as we translate it into a single value, and that single value is the difference. Let's move into an example. Question number 1, I'm going to grab my blue pen. Okay, so in question number 1, at age 9, it's actually really interesting. So at age 9, it turns out that the average weight and height for both boys and girls are exactly the same. A random sample of 9-year-olds yields the results below. Based on the sample results, can we conclude that the height of boys and girls at this age are the same? We're going to test at the 0.05 significance level. I want to go ahead and label these as sample number 1 and sample number 2. I've got my sample values. I want to go ahead and set up step number 1 as we move into our hypothesis test, our hypotheses. The null hypothesis is that there is no significant difference. If I subtract the 2, mu1 minus mu2, the difference is equal to 0. Another way of stating that would be that mu1 equals mu2. For the alternative, I need to go back and read the question. The question says, are they the same? So it doesn't say we think one is higher or one is lower, just are they the same? So my alternative, H sub A, is going to be that mu1 minus mu2, does not equal 0. Again, if I were to put this into an equation with those means on either side, this would say that the first average is different than the second average. But we're using the differences. Oh, and that's actually not step number 2. That was just hypothesis 2. Let me erase that. Now I'm ready for step number 2. Okay, so for step number 2, grab my blue pen. Come on. So for step number 2, I want to find my critical value. This is a z-test. I've given sample variances, but I'm going to go ahead and use a z-test here. We're going to be using z-tests for all of these just to keep things simple. As I look for my critical value, I need to go to table F, which I've got up here. There's table F. This is a two-tail test, and I'm testing this at 0.05. So two tails, 0.05. We're going to test this with a z under the normal curve, so I go all the way to the bottom, and I get 1.96. So plus or minus 1.96. Let me grab up our work again. So those critical values, I've got 2 regions, so I want plus or minus 1.96. And this gives me a normal curve with 2 significant regions, negative 1.96, positive 1.96, and my 2 regions here and here. My expected value has a z-score of 0. If I were to put this in terms of my differences, mu1 minus mu2, I have an expected difference of 0. Okay, step number 3. So for step number 3, I want to find my test value. We're going to use the calculator to do this. So to find the test value, I'm going to go into my stat menu, over to tests, and I'm looking for a 2-sample z-test. So right down there to number 3, a 2-sample z-test. I want to go ahead and put my data in. And the first thing it asks me for is a population standard deviation. I only have a sample variance, so I need to go back here and remember how to get from my sample variance to my standard deviation. The variance is the standard deviation squared. So to get to my standard deviation, I need to take the square root of my variance. So as I type this in here, I want to go square root, so second square root of, this is sample 1, so of 98. And it will just calculate that right in line for me. And the second standard deviation is going to be the square root of 120. And then I'm ready for my sample means. So that's going to be 123.5. And that sample size, this is for the boys, is 60. X bar 2 is 126.2. And that sample size is 50. We are doing the not equals for the alternative hypothesis, and I go ahead and hit calculate. So my test value z, let me go back to my blue pen. So my test value z is going to be that negative 1.34. So z is about negative 1.34. That lives right over here somewhere in my fail to reject region. So I'm going to fail to reject that null hypothesis. Step number 4 is fail to reject the null hypothesis. And step number 5, let's go back and read that question. Can we conclude that they're the same? So in this case, they're the same is my claim. So do I support that claim? I failed to reject the null hypothesis, which means I'm keeping the null hypothesis, and I am not keeping the alternative hypothesis. So there's no significant difference. I'm just going to write sig. So no significant difference. The claim in this case was the null hypothesis. So we can say that we support the claim. Okay, so as we're looking at these two different parts of our hypothesis test, this part right here, step number 4, our decision, this is always based on the null hypothesis. But when I go to step number 5 is based on the claim. So you want to go back up and decide, did I just keep the claim or did I reject the claim? So in this case, we did keep the claim. We'll look at some others, but step number 4, the decision is based on the null hypothesis, and step number 5, that summary, is based on which one is the claim. Okay, so there's one more piece of this one, actually 2 more pieces. So is there a chance of a type 1 or a type 2 error? Let me go back to my blue pen. We failed to reject, which means there's a possible type 2 error here. So this is part B. Possible type 2 error. That could be because of a small sample size. We're looking at their ages alone. We're not looking at when their birthdays are. Maybe some of these people are, maybe some of the kids are closer to turning 9 or 10 than others. So birth dates could be a factor, sample size could be a factor. Part number C is to take a look at the confidence interval. Where is it? Use a confidence interval to support the conclusion. So my conclusion is what I've circled there in yellow, that there's no significant difference. So my conclusion is actually saying that mu1 minus mu2 is equal to 0. We should find 0 in that confidence interval. So as I work through my confidence interval, I'm going to go back to stat, over to tests. I'm looking for a 2 sample confidence interval. So that would be, there it is, 2 sample Z interval, mine's number 9. And luckily it kept all of my stats for me, which is great. So I'm going to arrow through this. I do want 0.95, and I go ahead and I hit calculate. So as I look at this confidence interval, so if I were to write it, first of all, it would be negative 6.6 is less than mu1 minus mu2 is less than 1.24. On my number line, that would be from negative 6.6 to 1.24. So there's a 95% chance that the difference of any 2 samples that I grab of these sizes fall within this range. So I've got a 95% chance. This is 95% of differences. And it does so happen that 0 lives in that group of 95%. So it does support my conclusion because 0, which is what I found from my test, my expected difference, lives in that confidence interval. Let's go on to another example. Number 2. So number 2, the average sales price of a 2-bedroom family home in Ephrata and Quincy are shown below. Random samples of 40 houses in each region was examined. At the 0.01 significance level, can it be concluded that Ephrata's mean home prices are significantly higher than Quincy's? So if I call Ephrata number 1 and Quincy number 2, my claim here, can it be concluded? Here's my claim, is that mu1 is greater than mu2. This is going to be an alternative hypothesis. If I change that into a difference, mu1 minus mu2 is greater than 0. Let's go ahead and set up our test. Our null hypothesis, no difference. So mu1 minus mu2 is equal to 0. We already did the alternative hypothesis, and that's that mu1 Ephrata minus mu2 is significantly greater than 0. And in this case, my alternative hypothesis is the claim. So when I answer that very last question of my hypothesis test, I want to decide if I'm keeping the claim or not keeping the claim. Let's say I'm using a p-value method, so I can just go right into the p-value, step number 2. So for my p-value, I'm going to use my calculator to get there. So I'm going to go to stat and then tests. This is another 2 proportion z-test. enter. I want to go ahead and enter these values in. I was given the population standard deviation, which is great. So I've got 10,500. Oop, I don't want a comma there, do I? 10,500. And then my second standard deviation is 12,000. X bar 1, that's going to be 258,000. That sample size is 40. Second mean is 249,900 with a sample size of also 40. I want, for my alternative hypothesis, I want greater than. Continuing to arrow down, let's go ahead and calculate. Okay, my p-value is the second number there. So I end up with this 6.57, so 6.57 e negative 4, but this is scientific notation, 6.57 times 10 to the negative 4. If I were to write this one out, this one's not too bad. It would be 0.12367. There are 4 decimal places before I hit the 1 in scientific notation. This is a really, really small number. If I were to draw out my normal curve here, I've got a tail on the right because of that greater than. The area of my tail is 0.01. If I were to fill in the area starting from the edge of the tail, for my p-value, it just would barely even sit inside there. So it stays well within the rejection region. So our conclusion, let's do our decision first, actually. So step number 3, I still live in the rejection area. So I reject the null hypothesis. And I'm doing that because my p-value, so my p-value, it fits inside or it's smaller than my significance level. So it fits inside that rejection area. And then step number 4 is the conclusion. So for step number 4, do I support the claim or not? Well, now I am rejecting, so I'm going to go up here and cross off, I'm rejecting the null hypothesis in favor of the alternative, and the alternative is the claim. So for step number 4, we support the claim that Ephrata's average is significantly higher, I'm just abbreviating here, than Quincy's. Okay, so that takes care of part A. Part B, is there a possible type 1 or a possible type 2 error? Well, we reject it. So whenever we reject, so part B, whenever we reject, we have a possible type 1 error. So possible type 1. What could explain this? One of the things that could explain this is the fact that we use means instead of medians. Median is actually a better measure of home prices because we don't end up with those really, really expensive homes upping the average of the home price. So it could be the use of means instead of medians. And we are not going to learn a way of testing the median, so we would just live with that, right? Again, you could always say a small sample size. You could also say that the sample size was not very randomly chosen. Maybe it was all within a certain neighborhood instead of randomly throughout the region. Lots of possible reasons for that type 1 error, not that it's even necessarily an error. Okay, part C. Part C says use a confidence interval to support your conclusion. So let's go ahead and build. In this case, alpha was 0.01. So we want to build a 99% confidence interval. And that just takes 1 minus 0.01. That leaves me with a 99% confidence interval. So I go to stats, over to tests. I'm going to grab that 2 proportion z interval. There it is. And it remembers my numbers. So great to do this together. And I do need to change, though, the confidence level, 0.99, and then I calculate it. So I end up with, let's see, 1605. Remember, this is the difference in the home prices. mu1 minus mu2 less than 14,594. 14,594. So I expect the difference of home prices to be somewhere between $1,605 and $14,494. If I were to put this onto a number line, my expected difference is between $1,605.90 and $14,594. Let's go ahead and highlight this guy. So with a 99% chance, the home difference is going to be between these two numbers. 0 does not live between these two numbers. 0 is over here somewhere. So we're not expecting a difference of 0. We are expecting a significant difference. So based on our confidence interval, we are expecting a significant difference. Just enough room, significant difference. So it does support my conclusion. Okay, number 3. A researcher wishes to see if there's a difference between the mean number of hours per week that a family with no children spends watching TV compared with a family that does have children. She selects 2 random samples. Results are below. We want to see if there's a significant difference between the means. So as we set this guy up, null hypothesis is always the same. mu1 minus mu2 equals 0. Let's do no children as 1 and children as 2. So our chart's set up just a little bit differently here. Our alternative hypothesis, the question is just, is there a difference? So there either is or there isn't. So this would be mu1 minus mu2 is not equal to 0. So it's going to give me a two-tailed test with 2 rejection regions, 1 on either side. We want to use the p-value method again, which is great. I don't need to use the table at all, so I can just go right to step number 2 and put this into my calculator. So stats and then tests. I want that 2 sample z-test. And let's go ahead and just work through our input. Starting with, there we go. So starting with the first, let's see, so population standard deviation 1 is going to be 2.2. Standard deviation 2 is 2.8. The first sample mean is 8.9 hours a week, and that's a sample size of 23. And for our other group with children, we've got 10.1 hours per week, and that was also a group of 23. This time we do want to choose, there we go. So we do want to choose not equals to match our alternative hypothesis, and we'll go ahead and hit calculate. So step number 2, we're looking for that p-value. So that p-value area is 0.106. We had 0.05 split between those two areas. So if I split my p-value area of 0.106, it's bigger than 0.05. So on both ends here, the p-value areas are doubled for these tests. I'm going to spill into my fail to reject region. And this is because, there we go, my p-value area is bigger than my significance level. 0.106 is bigger than 0.05. So I spill into the fail to reject region. So that gives me step number 3, fail to reject. So I'm going to fail to reject that null hypothesis, which means I'm keeping it. Let's go ahead and mark which one is the claim. So it says, is there a difference? So to see if there's a difference, we're going to state that second one as the claim. We are not keeping that claim. So for this last part, step number 4, We found that there's no significant difference. So we do not support the claim. That there's a difference. I'm just going to talk through parts B and C. So is there a possible type 1 or type 2 error? We failed to reject, which means that there's a possible type 2 error. We can also use a confidence interval to support this conclusion. So we go do that by going to stat and then tests, looking for that 2 sample, there it is, 2 sample Z interval. With any luck, yep, it keeps all of my numbers. So I go ahead and keep everything but the confidence level, and that's going to be 0.95 to match the 0.05. So my confidence level is going to be 1 minus 0.05, so I need a 95% confidence interval. Go ahead and hit calculate. And we end up with a confidence interval that goes from negative 2.655, crosses over 0, and goes to 2.557. So this confidence interval, I'm just going to draw it up here on my number line. So it's right next to our null hypothesis. So this is negative 2.66, and it goes to 0.255. So there's a 95% chance that any of these two groups of 23 is going to have a difference somewhere between negative 2.6 and 0.255 in their average viewing hours for the week. And 0 just happens to live right in that interval. So we are expecting, along with those numbers, a difference of 0 with that 95% probability. So finally, we want to look at an example where we're testing proportions instead. Everything is very similar, so that's why we're just going to do one of these examples. What I want to do, though, is to set up what we need to put into the calculator. So we've got a sample of 200 men and a sample of 300 women. So I'm going to go ahead and set up a chart here. So we've got men, and we're going to call them sample number 1, and women, we're going to call them sample number 2, just because of the order that they came in our problem. So as I put this together, I've got the sample sizes 200 and 300, and I have the favorable outcome. So this is going to be my x, not x bar, this is just my favorable outcome, the number. So my favorable outcome, so this is going to be x1 equals 130, x2 is equal to 63. So as I go through and label, I can label these also as N1 and N2. We don't have a standard deviation for these, so this is all that we need to put into our table. I do want to do one more thing, and I want to put together what those proportions look like. So my sample proportion, or percentage, is going to be, this one's going to be 130 over 200. This is really nice because it doesn't give you the average, and we can't just start by looking at what the difference would be. So 130 minus 200, divided by, gives me, so that first sample percentage for the men, so 65% of men in that sample wore seatbelts. For the women, 63 out of 300, it's not going to be that great, right? So P2 is going to be 63 out of 300. So let's do that as well. So 63 divided by 300. And we end up with a much smaller percentage. So P2 hat of 21%. So it looks like we have a pretty big difference, don't we? So our sample difference, P1 hat minus P2 hat, is 65% minus 21%, which is what, 45%? It's a pretty big difference. So I'm expecting to find a significant difference as I test based on these values. So let's go ahead and do our test. And I'm not going to have enough room, so let me erase this right here, because what we really need are those other values to put right into the calculator. Okay, and then we've got those sample percentages over there on the side. So step number 1, I need my hypotheses, very similar to the means, but this time they are proportion. So P1 minus P2 is equal to 0. My alternative hypothesis, let's go back and read this, are men more safety conscious than women? If they are, they're going to have a higher percent. So that would say that P1 is greater than P2. If we put that together as a difference, P1 minus P2 is greater than 0, just moving P2 to the other side. Let's do a p-value, yay. So step number 2, the p-value area is what we're looking for next. And we're comparing that to a significance area of 0.01. I go into stat and then tests down to a 2 proportion z-test. There it is. Okay, so I want my favorable outcome for sample 1, that's the men, so that's going to be 63. Oh, sorry, not 63, 130 out of 200. And for sample 2, that one is the 63 out of 300. And for my symbol, I want P1 greater than P2 in the alternative hypothesis. I arrow down and I hit calculate. And we end up with a p-value area of about 2.11 e, so that's times 10 to the negative 23. If I were to write this as a decimal, I would need 23 decimal places before I got to that guy. 211. This is a super duper tiny number. It is going to fit well within my significance area of 0.01. So step number 3 for my conclusion, I stay well within the rejection region, so I reject the null hypothesis. Step number 4, test the claim that men are more safety conscious. Okay, well, what was our claim? Our claim was actually, let me grab my red pen, it was the alternative. Come on. There it is. So this was my claim. Men were more safety conscious. I am rejecting the null hypothesis, which means I'm keeping the alternative, which happens to be the claim. So for my conclusion here, I do support the claim. So these proportion tests are done very, very similarly to the mean tests. Let's also run a confidence interval here, even though it didn't ask us to. So we're going to go stat and then tests, and I'm going to arrow down to my 2 proportion, there it is, z interval, enter. And it keeps all my numbers, which is great. My confidence level, though, I have a 0.01 significance level, so my confidence level is 0.99, and then I hit calculate. And I end up with these differences between 0.33 and 0.54. 0 is not in there, so I'm not expecting, remember I crossed that out, so I'm not expecting a difference of 0, and it doesn't live in my 99% confidence interval either. So we see that the confidence interval also supports the work that we did.